Hello folks, this is a quick video about sampling scopes and generating short rise time pulses and measuring them and equivalent time and real time. And what you see here is an old school HP 54120B, and this is called a digitizing oscilloscope mainframe. Sounds very good. But if you just buy this on its own, you'll notice that there's nowhere to plug your probes in, and so you need to have an additional item which is called a test set, and you can buy different ones, but probably the most common one is this test set here, which is an HP 54121A. It's a 4-channel test set, and you'll see on there that there are well, the 4 channels. You'll also notice that they're not BNC connectors. What these are 3.5mm connections, which are actually they're compatible with SMA connectors. They're slightly different because they can go up to a bit higher frequency than SMA connectors. They managed this by having removing some of the dielectric from the inner of the connector. So you'll also notice that I've got these little things on the end. These are actually homebrew. What they are, they're Edge SMA males, and what I have is they're just short in the connections, because you need to be a little bit careful with static on these devices. It's a maximum 2 volts on any input, and because of the nature of the front ends on these things, you've got to be careful and take relevant precautions with your anti-static, as of course we always do. So I'm just going to show you as well. We're just going to have a look at this connector, and hopefully I don't get in the way too much. But you also notice I've got a special spanner here. This is an SMA connector, so an SMA torque spanner, which has just got itself stuck onto a magnet. And not sure if you can see that in focus or not. This is a Suna torque wrench, and the reason for this you'll see in a moment, but it's designed to be used with SMA connectors and also these 3.5mm connectors that I mentioned. Now, what's the difference? You'll see that they're quite dark inside, and the reason for that is that unlike normal SMA connectors, they don't have the dielectric that I mentioned earlier on. So if I show you a typical SMA female, which I'll just put up here against it, you'll see there's some white Teflon in there, whereas these 3.5mm connectors don't have that, and it just means they can go up a little bit higher in frequency. Now, the other thing to note on this is that you'll see there's a gold bit and then a sort of silvery bit. Well, these connectors just here are actually savers. So they're just inline bulkhead female to female 3.5mm connectors. And the idea is that because you're quite likely to be screwing and unscrewing your probes and various bits of test onto these, it means that you don't break the connectors, because they're a little bit delicate. So the connectors in here, if you're going to break anything, you're going to break the saver just here. So if you do buy one of these, I would do your utmost to make sure that they come with these savers. You can normally tell from the photograph, but check that they do have these savers, otherwise you might have this supposed bargain might not be quite the bargain you thought it was. So here we go again. You might notice that since you last saw the display on the oscilloscope, it's slightly changed, and the reason for that is that I've unplugged this connector here. So I have the oscilloscope set up in what's called time domain mode, and what happens there is that on channel 1 it spits out a pulse with a very fast rise time, less than 45 picoseconds, and then what it does is it also listens on this port as well. So what you can do is, while it's transmitting the pulse, it's actually seeing what's going on, what's coming back in this port. And you'll see that if I put this short back on here. This is not actually a termination, a 50 ohm termination, it's actually a short. If I put this short back on here, you'll see that that's what happens when you get a short. Now what are we measuring here? Well, if you have a look at this, this is the start of the pulse that it's measuring. The pulse actually has happened way back here somewhere, around about 15 nanoseconds or so earlier on. But there's a delay internally between the trigger and this actually displaying on the screen here. And what's happening here is that's the first trigger, that's the first pulse going out, and then there's a short delay here, and you'll see this is 500 picoseconds per division, so about 750 picoseconds later it gets to where the short is. So that's purely down to the propagation delay through the cabling. So if I unscrew this again, take care, there you go. And that's what happens when it's open circuit. So you can tell the difference if you've got a piece of coax with a short on it, which it would have it down here, or an open. So what I'm going to do is show you a little bit more of that. So I'm going to add on a short piece of coax here. Oops. Not very easy with the camera in the way. The camera is right between my my two arms, so not the easiest. There's a couple of things I want you to sort of notice here, and I'm going to do it up with my torque wrench. You'll hear it click when it has just the right amount of torque. There you go. And you'll also notice, first of all, that it's a lot longer. This is an open end here. It takes a lot longer for it to see this open end of the coax. So you can actually measure your length of coax if you really wanted to by using this. And what I should add is that the speed of the electrons down here isn't the same as the speed of light. It's actually less than that. But also what you're measuring here is the round trip time. So you're not actually measuring the time it takes from here down to the end here. You're measuring the round trip time that the signal took to go from here all the way down to here, and then back again into the test set. So we could make a measurement on this. If I get the cursors, I'm doing a delta T, and we'll do the stop marker. And you can see the delta T here is 2.53 nanoseconds. Now I'll just mention where you'll see that the start marker was here. This was actually where the this point here, and you'll see there's a very tiny bump just here, and that's purely down to the fact that there is a slight impedance bump at this point here. This isn't actually too bad, although the really expensive cables, which are hundreds of dollars, you'll have difficulty seeing any impedance bump at all on them, but you can see a lot worse, and we'll see some of that in a moment. So here's the cable here, and what I'm going to do now is I'm going to plug it into channel 2, and we'll have a little look-see to see how it looks on channel 2. So I'm going to undo this short, and we'll plug this in here. Take care, by the way, when you plug these in, there's a bit of a rule of thumb here that you shouldn't actually twist the cable itself. You should only turn the nut with your torque wrench, and you'll see again there's a little bit of an impedance bump just here. Not too bad, I've seen a lot worse. So let's get channel 2 up and see what that's got. So hit channels, channel 2 on. There's our channel 2, and if I get the markers up again, wherever they were, delta T, stop marker. So that was a stop marker that we had. And if you remember, I was telling you that that was actually measuring the round trip time. So hopefully what we're going to do, that was 2.53 nanoseconds. If I now move this stop marker back to here, hopefully it'll be around about half of that. There you go, good enough, 1.25 or so. Anyway, so that gives you a little bit of an idea of how to look at things in the time domain. And so next thing I'm going to do is show you a little bit about the rise time and how good the rise time is on these devices. So what I'll do is I'm going to just switch the time base. I'm just going to move the signal around a little bit. So we've got her in the middle. I'm going to really zoom in here. There we go. So we're now at 10 picoseconds per division, which is pretty nice actually. I think what I'm going to do as well is I'm going to change it so that instead of doing persistent, we'll go for an average. Okay, so next thing to do is I'd like to see what the rise time is on that. So the spec on this scope is a rise time of the TDR pulse output is less than 45 seconds. But measuring that, it's not quite as simple as that. You have to think about the whole system, because the channel test set on the oscilloscope itself also has some rise time delay in that. So you have to take that into account as well. So what I can do is if I measure I'll just check we're on channel 1. Yeah, we are. Measure the rise time here. 33.4 picoseconds. So I'd say that's pretty good in anybody's book, because the spec is actually 45. Less than 45 picoseconds, and the channel test set has got, I think on this channel is around about 20 picoseconds, and you don't actually just add them together. You take the like I do a Pythagoras on it, so you square the two times and then root them, and then you get the expected time of the system rise time. So that's pretty good. Quite happy with that. Now the next thing I want to do is to show you what it looks like on channel 2. So I'm just going to zoom out a little bit, a lot in fact. There we go, I did too much then. And there we go. And I'm going to move it and we'll zoom in on the... You can see this is an old scope and it takes some time just to do its business. And we're going to zoom in on this and we'll see what the difference is, just because it's gone through this little bit of cable. Let's see if we can get it up to 10 picoseconds. There we go. So we're at 10 picoseconds per division, and now what I'm going to do is I'm going to measure that as well. So if we go to measure, select channel 2, and we want rise time, 37.8 picoseconds. So not bad. But it is longer, and that's a result really of the fact that the cable will have some loss in it, and the loss gets worse at high frequencies, and so that will show it up in its rise time delay there. So that was great, but obviously a short cable that we had earlier on is not really any good for probing, so I've now got a longer cable here which we can use, and we can poke into some other oscilloscopes and see what that rise time looks like. And you'll notice here there's a little bit of a longer delay. This is actually 1 nanosecond per division here, so if I get the marker, the T markers out and get the start, so remember again that's where the actual start is, that little kink just here, which is the cable interface just here. And then normally what I'd probably do is actually get that measured up a little bit more accurately, but I'm just going to give you an example. So this one's actually got a delta T of just over 4 nanoseconds on the cable, which looks about right. That looks to me maybe a couple of feet or so if you get the velocity factor into account and everything there. It probably works out to be about that 4 nanoseconds or so. So we're going to take this. We'll also have a little look as well. Sorry, I forgot to do this. At what the rise time is on this cable as well. Notice it's a little bit thicker. What you quite often find is on the thinner cables, the problem is the losses become so significant but it actually makes it difficult to make a reasonable rise time at the end of them. So we're just gonna measure that. Let's just move the time base so that it's in the middle. There we go, and we'll zoom in and we'll measure this rise time. Let's just move it back again a little bit. Okay, let's measure rise time. Oops, might help if I selected the correct channel. There we go, so we've now got a 44 picosecond rise time. So that's really just to demonstrate that by putting that cable on there, because of the frequency response of it, we're going to get a not quite as good a rise time as you would have got if you're actually measuring right at this point here. But 44 picoseconds is going to be pretty good, because the oscilloscopes I'm going to show you have got specified rise times underneath 400 picoseconds, well, around about 400 picoseconds. So we're almost an order of magnitude different here. So hopefully this 44 picoseconds won't have a huge impact on what we're going to demonstrate with more day-to-day oscilloscopes. So of course I couldn't do one of the Rigol DS1000Z series, so here you go. This is an upgraded MSO1074Z, and so we're getting a rise time of about 2.3 nanoseconds of that sort of order, which is actually pretty good. That's about 150 megahertz if you do the 0.35 over time to calculate the bandwidth from the rise time. So that's actually pretty impressive. You'll also notice that on here I'm feeding it through a 50 ohm feed through as well. This scope is the only scope that I've shown you which doesn't have the 50 ohm option on it internally, and so you have to provide your own. This was never going to be complete without a 2467 or indeed the cat walking across the shop. But this here is a wonderful Tektronix 2467 scope. Now, one thing I noticed about this is the second time I've had to take this shoot. Unfortunately, there's a bit of drift on it, so I keep having to adjust the rise time settings. But the first thing to note here is that you'll notice I've carefully adjusted the amplitude of the signal and the position of it on the display, so that the final setting and the initial setting are on this dotted line here. I hope you can see that dotted line, and I will zoom in a little bit to see if we can get a better view of that. So you see on this dotted line, this is the beginning of the trace, and the dotted line here is the end of the trace. And the reason is that it makes it easy to be able to move your cursors to be able to do this. You'll see that even in the time that we've been talking, there's been a little bit of drift. So I need to first of all, I'll adjust it so we get the first one just at this line crossing here, and we want the second one at the line crossing there, and actually it looks about okay. So I've got about an 880 picosecond rise time on my Tech 2467B, which is reasonable. So here's another example. This is an MDO3000. It's an MDO3014, which is a 100 megahertz version, but it's been upgraded to a 500 megahertz version. So let's have a look at this and see what the rise time is according to the measurement settings. So if we press measure, add measurement, and let's just scroll down, and I always get the wrong thing here. Okay, add measurement. You do get used to this, but oh dear, quite what they were thinking when they designed this, I don't know. Now, one of the problems is you'll notice this rise time's a little bit all over the place, and it does seem to have a problem. I've tried all sorts of things, for example changing it to doing averaging and various other options, but none of them seem to be any good. So what I'll do is I'm just going to do it with cursors, and we'll do it similarly to the old 2467. I've actually set this up so we've used the vernier so that we've got exactly 5 divisions between the end state and the beginning state, so it makes it easier for us to get the cursors set there. So if I just bring the cursor in, there's a cursor on the left, and I'm looking for it just when it crosses this line just here. Is that about it? Okay, and then we'll do the second, bring the second cursor in, and that's just about that looks about it. Okay, so we've got the 2, and the difference in time is just here. So that's 640 picoseconds, which actually is pretty good. I'm quite impressed with that. That's not bad at all. Quite good. So here's an Agilent DSO7104B, which is a 1 gigahertz scope and 4 gigasamples per second, and this is just set up as default, and I haven't done any changes other than the time-based settings, and we're getting a mean rise time of 333 picoseconds, which you can see just here. Now there's some things we can do to this to improve it, and one of those things is to change it. Rather than being in real-time acquisition, we can use what's called equivalent time. And so what I'm going to do here is to switch onto the acquire menu and switch that off, and you'll see now that the rise time has gone down to just there. If I get the measure menu back on there, and what I'll do is I'm just going to clear the statistics here, and you'll see you've got a 275 picosecond rise time, which is actually pretty good. Another thing to note here that you'll see is that there is definite overshoot here, and that could be due to a number of things. It could be inside the oscilloscope, but because we've turned off real-time sampling, so there's no sine over x over x interpolation going on. So I would imagine this is something in the analog side. Now, could be in the amplifiers. Equally, it could be due to this transition here that we've got between the SMA and the BNC. And in fact, if I just move this up to the scope up here where the signal's coming from, you'll see here there's a bit of mess here. This is the transition. If I unplug, I'll tell you what, I'll zoom in a little bit on that. If I unplug the BNC, okay, so that's your unplugged situation. And then I'll plug it in again, and you'll see this is definitely an impedance bump here, and you can see it on the tracer. That's definitely bumpy. So this scope's been quite a pleasant surprise actually when measuring rise times. It's an Infinium 54831D MSO. It's actually a 600 megahertz specified scope, 4 gigasamples per second. And I'll tell you why it's been quite an interesting one, because there does seem to be quite a marked difference between what it can achieve in real-time sampling and what can be achieved in equivalent time. And being an Infinium level scope, it has lots of settings which on sort of lower end scopes you don't have any access to. It's all sort of hard baked into the firmware. So you'll see here we've got about a 470 picosecond rise time, which is this is with the default settings, and nothing really much excitement there to sort of write home about really. But then I'm going to show you something. So if I instead start setting up the acquisition, and I put it into equivalent time like that. And what I'm actually going to do here is I'm just going to reset the rise time for you. There we go. You see it's dropped down to 278 picoseconds, and you're in the gigahertz territory here.
and I can make it a little bit nicer by putting on averaging and whatnot. But this is essentially a 1 GHz scope territory that we're talking about here with this sort of rise time. And you'll notice, as with the Agilent DSO7104B, that had quite an overshoot in there. So I suspect, again, there's some jiggery pokery going on there in the either to do with the mismatch here on the impedance bump on the BNC, or internally in the amplifiers, perhaps maybe overshooting. But yes, quite impressive. So what have we got there? 288 peak seconds. I say that is gigahertz, 1 GHz territory for oscilloscopes. So pretty happy with that, I have to say.